And I want to make clear, this will not be a conventional technical talk on my own research, but a very big picture, top-down view of the planet. And my hope today is to help you see this familiar old planet through new eyes, to achieve what Bertolt Brecht called the Verfremdungseffekt, defamiliarizing the familiar. So I'll share my screen. In my experience, most people walk around on Earth like bad tourists, enjoying its amenities without ever learning its language or customs, which I hope to convince you are subtle, sophisticated, even elegant. Imagine if you knew nothing about the history, traditions, and idioms of a place where you spent years and years of your life. Your everyday existence would be greatly diminished, impoverished. This is sadly the relationship many Earthlings have with their dwelling place. And while this is, in my view, tragic, there are even more serious practical implications of such widespread geo-illiteracy. Namely, most of the environmental problems we face today arise from this collective ignorance of the planet. If you start recklessly intervening in an old system whose habits you know almost nothing about, of course you will do it damage. And of course, the system will begin to behave in unpredictable ways. As I said in the abstract for my presentation, this is a talk I would like to share with rich and powerful people who are treated as prophets and visionaries, but seem to have absolutely no clue about how the planet works. It's truly remarkable that a set of interacting atmospheric, biological, hydrological, and tectonic processes has kept Earth on an even keel for most of the past 4 billion years. But it's also a fact we simply would not be here to marvel at these things if they hadn't. These long-lived geologic systems have a thing or two to teach us about durable design and should instill in us a bit of reverence for the logic of the Earth. Let's start with some historical perspective on studying the Earth. We humans, especially in the West, have long struggled to see the Earth and our place in it in proper perspective. Some attitudes we still have toward the Earth, I think, are traceable back to the Greeks and their concept of nested celestial spheres, with the spheres of divine truth, the eternal, immutable heavens, being furthest from the corrupt, constantly changing earthly realm. These ideas later permeated early Christian teachings that the earthly and secular are not merely imperfect, but defiled, the antithesis of the sacred. Monks and missionaries sought to purge every vestige of nature worship from the populations they converted. Old pantheons that were deeply embedded in the landscape were replaced by an abstract, non-localized God and a theology that depicted this world and even our bodily selves as corrupt temporary dwellings where souls could lose their way en route to heaven. And I think in some strange way, these ideas still permeate scientific thinking. Fields like physics, focused on the timeless and universal, are privileged over the study of timeful, evolving entities like the Earth. The scientific study of Earth had an early flowering in the Enlightenment period as a number of visionary natural philosophers, especially James Hutton in Scotland, Alexander von Humboldt in Germany, and Charles Lyell in England, began to see evidence of the antiquity and complexity of nature. And I don't have time today to talk about some of the details of what these people did, but I want to just mention James Hutton in particular. He's often pointed to as the father of geology, primarily because he recognized deep time in a time when, at least according to the Bible, people thought the Earth was 6,000 years old. Hutton very radically proposed that the Earth was infinitely old. And this lithograph up here on the left is a depiction of an outcrop that Hutton documented on the east coast of Scotland, close to the border with the north of England. What you can see is a sequence of sedimentary rocks that are tilted on edge, and then kind of a rubbly layer, and then another sequence of rocks that are horizontal. And Hutton, in a time almost 200 years before we had any understanding of tectonics and mountain building, recognized that these tilted rocks were the deeply eroded remnants of a mountain belt. And this rubbly layer represented essentially the time it would take to erode a mountain belt to sea level, and then a another succession of rocks was laid down on top. So when he saw this rubbly layer, he recognized that this was an immensely long period of time. It would have taken far more than 6,000 years to erode a mountain belt, and essentially postulated that the Earth was this infinitely cycling, rejuvenating, almost cyborgic kind of creature. So Lyell then kind of codified some of the methods of geology and wrote this book that was hugely influential, and in fact became a great influence on Darwin, the idea that we can understand the Earth and features on it if we think about the power of time and incremental processes to achieve great things. So for a short time in the early 1800s, geology enjoyed a golden age when the idea of deep time captured the public imagination in a way that space exploration does today. But when Darwin, who was again inspired by Lyell and this idea of incremental change, when Darwin, who considered himself as much a geologist as a biologist, suggested that humans were just another twig on the tree of life, the honeymoon for geology was over. The backlash against Darwin was ferocious and came not only from the clergy, but also very much from the preeminent physicist of the day, William Thomson, or Lord Kelvin. Kelvin rightly dismissed Hutton's idea of an infinitely old Earth as a violation of the laws of thermodynamics, essentially he said, Hutton was talking about a perpetual motion machine. But within a year of Origin of Species, Kelvin issued the first in a series of papers estimating the age of the Earth based on calculations of how long it would have taken the Earth to cool from a molten state through conduction, and also some papers on how long the sun could have been burning. But this is, of course, long before physicists actually understood what made the sun radiant, namely fusion. Kelvin's estimates for the age of the Earth started at around 400 million years in 1860 and grew progressively shorter in the next decades, plateauing at around 20 million years. And again, his estimate, his approach to estimating the age of the Earth was to assume that it had started from a molten state and had cooled progressively by conduction. There are two problems with that. Today, we understand that the Earth cools itself mainly through convection. Rocks are very poor heat conductors, but also the Earth has not only cooled, but there is a big inventory of radioactive elements that have generated additional heat since its formation. But because of his stature at the time, and frankly, the inability of many geologists to understand the mathematics of his arguments, his proclamation that the Earth could only be 20 million years old was a seemingly immutable fact to many geologists. And this was a really troubling thing. Darwin called Kelvin his sorest trouble because he and others felt in their bones, based on geological and biological observations from the rock record, that the Earth must surely be at least hundreds of millions to billions of years old. And sadly, Darwin died with real doubts about whether his concept of evolution by natural selection could be true on an Earth that was only tens of millions of years old. So several generations of geologists from essentially about 1860 to right around the turn of the last century labored under the constraint of Lord Kelvin's pronouncement. And it had profoundly damaging effects on the progress of geology. I think of the second half of the 19th century as essentially the dark ages for geology. Meanwhile, of course, physics was going from strength to strength, and its reductionist approach became the template for the way science should be done, dissecting messy reality into timeless, idealized parts that can be manipulated in experiments or equations with very precise solutions. And of course, this is a very powerful way to investigate some things, but not a big, old, complicated thing like a planet. So between about 1860 and the 1960s, many geologists retreated into the safer tax of taxonomy, classifying and cataloging the many minerals and rocks and fossils, or to the grimy business of locating coal and ores to fuel the roaring engines of capitalism. So at a time when physicists were unlocking the secrets of the atom, geologists could offer no grand unifying theory of the Earth. And unfortunately, geology is still shackled by the public perception that the field acquired during this period, the reputation for being a dull science whose subject, by extension, must be dull. Meanwhile, the vastness of the universe was being discovered, and this too seemed to demote the Earth even further. It's just a tiny speck among billions of other solar systems. And all of these ideas in turn about the Earth as an unremarkable, inert planet with an irrelevant past have played nicely into our worship of free markets and the belief that we have invented the world and are somehow exempt from the laws of nature. And this in turn leads to dangerously distorted perceptions about our technological abilities, including the belief we could surgically engineer the climate without a torrent of unintended consequences or terraform Mars in a matter of a few human generations. Such thinking reflects profound ignorance of both nature and human nature. How could we possibly think that we could control a planet when we haven't managed to govern ourselves? We're prone to confusing cleverness with wisdom. It's only recently that we've begun to see the full complexity of Earth's hidden infrastructure. And it gives lie to all the old notions about the planet. It is not a dull and inert place, but responsive, resilient, robust, and incredibly complicated. So how did it get to be this way? There are now more than 4,900 known exoplanets, and in popular media coverage, there's always a lot of hoopla about ones that lie in the habitable zone, where liquid water could exist, which is probably a necessary, but certainly not sufficient criterion for life. The composition of a planet is also important. Even after almost 14 billion years of stars manufacturing heavy elements, the universe is still mostly just hydrogen and helium. Rocky planets like the Earth, with the full complement of 92 elements, are fairly rare. Another thing that's not always appreciated is that for life to arise and persist long enough to diversify, a planet has to be affiliated with a long-lived star. And I'm sure I don't need to explain the Russell-Hertzsprung diagram to this group, but arguably you could not have a complex biosphere emerging on a planet whose star only had, say, 10 million years before it blew itself up. And then being in the zone where liquid water can exist at the surface does guarantee that water is in fact, does not guarantee that water is in fact present or abundant, or that it would be retained over long time periods. Earth has had abundant water from early on, a mix of primordial water from its formation and water acquired early on from comets. But more importantly, it has retained that vast inventory of water for more than 4 billion years. And this leads me to my main idea, that it's not just the primordial attributes of the Earth that have made it such a commodious place, but the habits it has developed and practiced over the eons that make it so remarkable. And the two most important habits are biogeochemical cycles that involve the biosphere, atmosphere, hydrosphere, and to some extent the solid Earth as well, and plate tectonics, which involves especially the hydrosphere and solid Earth. And they're connected in subtle ways. So let's look at biogeochemical cycles in a very top-down way first. Other than a fine rain of comets, micrometeorites, and the occasional dinosaur-killing asteroid, Earth has not acquired any significant new mass over the past 4 billion years. Yet the median age of surface rocks is only about 500 million years. The oceans are refreshed every few thousand years, and soils are constantly washed to sea but haven't yet disappeared. That means that everything on the planet is incessantly recycled. The water, air, soil, the very crust of the Earth, at very different rates, are constantly being reused and remade via evaporation and precipitation, photosynthesis and decomposition, melting and crystallization, erosion and mountain building. Every process has an inverse operation, every flow a compensatory counterflow. It's like a colossal and complicated contra dance in which after many rounds, everybody ends up back where they started. Biogeochemical cycles are complex and the study of them is comparatively recent. But there are a number of fundamental ways of quantifying their dynamic nature. One is the recycling ratio. It's defined as the amount of a commodity, like the elements calcium or phosphorus, that come into the biosphere from a geological source, rocks, in a given period of time, compared with the amount that is reused within the biosphere. This is essentially equivalent to the number of times the commodity is traded between organisms before becoming locked up in sediment or returning to the atmosphere. a resource that is reused many times via transport between organisms. For example, soil microbes, plants, herbivores, carnivores, scavengers, decomposers, before leaving the biotic system will have a higher cycling ratio than one that is taken in and discarded after a single use. So you can look at the very different values for calcium, potassium, and phosphorus here. The values of natural cycling ratios vary over orders of magnitude depending on what systems and resources one is considering, but they always are inversely correlated with availability. That is, the biosphere fiercely conserves and recycles the scarcest elements. So in this case, of these elements, phosphorus is by far the scarcest. But when a normally very scarce commodity like phosphorus suddenly becomes available, the dynamic equilibrium of biogeochemical cycles is profoundly disrupted. The contradance choreography becomes confused, and the result is ecosystem chaos, like the anoxic dead zones in the ocean. And this is a map of the Mississippi River drainage system, really the heart of the United States, with the Gulf of Mexico down here. Here are the Great Lakes in the north. Just showing the growing area of anoxia in the Gulf of Mexico that has been caused by badly managed use of fertilizers, especially phosphorus, coming in, washing off the fields, coming into the Gulf of Mexico, where there's just a bacchanal of consumption by microbes that then decay and suck all the oxygen out of the water. So this area of dead zone in the Gulf is growing. It's essentially like what the Black Sea is. A second important index in the study of biogeochemical cycles is residence time, the average time that an element or molecule spends in a given reservoir. Like cycling ratios, the values vary over many orders of magnitude. So you can see water in the atmosphere has a very short life span. It's at least in the shallow, or in the most parts of the atmosphere, a given drop of water will only stay for 9 days. In the ocean, this is the average value. It kind of depends on shallow versus deep, but this is the global value, 3,000 years. Mantle, 100,000 years, 100 million years, sorry. So vastly different timescales represented. And I just want to mention, I'm not going to talk too much about climate change today, but the Earth's long-term carbon sequestration strategy is really to form limestone. And most limestones on Earth are in fact biogenic products made of tiny little exoskeleta of zoo and phytoplankton like these coccolithophores. So this is what's storing carbon over the long haul over hundreds of millions of years, carbon dioxide that was originally exhaled by volcanism. A third metric, of biogeochemical cycles is the idea of mixing time, the time that it would take for a given component in a reservoir to become homogeneously distributed. And so if the residence time, which we just talked about, is significantly shorter than the mixing time, then you will get heterogeneity in the concentrations. So for example, phosphorus can be very variable in its concentration in seawater, or sulfur dioxide that's churned out by coal burning power plants will basically stay close to the site where it was emitted. But if residence time is large compared with mixing time, there's plenty of time then for that commodity to be distributed. And so, for example, CO2 in the atmosphere, it's very convenient that it has a longer residence time than mixing time, so our emissions do not pile up near us. If they did, we might be more motivated to curb them. So geology reminds us of our physicality, that we are deeply corporeal participants in biogeochemical cycles. And that is something to celebrate, a source of feeling of kinship with the rest of the natural world. It's also sobering, though, to realize that all of the great mass extinction events of the past 500 million years are linked with major disruptions to these biogeochemical cycles. Even the dinosaur extinction event, which of course is linked with a meteorite impact, was ultimately caused by the ensuing upheavals in the chemistry of the atmosphere and oceans. And the bedrock story of the greatest mass extinction in Earth's history, which is here the end Permian extinction, tells how a thriving global biosphere was dealt a nearly mortal blow by the combined effects of abrupt volcanically induced greenhouse warming, ocean acidification, and widespread marine anoxia, a scenario that's chillingly familiar to those of us living in the Anthropocene. In a mass extinction, the normally meticulous scalpel of natural selection, as Darwin described it, excising a particular color of moth or a finch with a suboptimal beak shape, becomes a machete, cutting down great swaths of the biosphere across many trophic levels. And it's invariably the large, specialized, top of the food chain organisms with huge energy needs who take the most serious hit. Luckily, though, the Earth is resilient, and little by little, ecosystems eventually recover with new dancers, but dancing very similar dances. And it's happened at least 5 times in the last 500 million years. So biogeochemical cycles are one remarkable habit that the Earth has developed and maintained over the long term that has helped keep the ocean atmosphere system on an even keel. Now let's turn our attention to the solid Earth, in particular the plate tectonic system, and explore how it too is intimately connected with the atmosphere, biosphere, and hydrosphere. So we noted already the idea of residence times and how they vary over orders of magnitude. The ones in blue are really the shorter term pace of the biogeochemical cycles. And for water in the mantle and carbon in limestones, this is telling us something about the characteristic pace of the solid Earth. These are sort of the Tai Chi pace of plate tectonics. Subduction, the way the solid Earth works, is the way that the exterior and the interior of the Earth remain in connection. This process by which ocean crust, born at mid-ocean ridges, is then returned to the mantle was not discovered until 1968. But the most important function that it serves in planetary stability is re-volatilizing the interior of the Earth, taking water in particular, and to some extent carbon dioxide, back into the interior. Most people hardly give the process a thought unless you happen to live along a subducting plate boundary and face the prospect of magnitude 9 earthquakes. But as we'll see, this process of subduction is central to the longevity of Earth's atmosphere and hydrosphere. When plate tectonics was first recognized, it was then assumed by geologists that there would be evidence for it found on other rocky planets and moons. But we're finding that Earth-style plate tectonics is not at all an inevitable fate for rocky bodies. So let's talk about the criteria for developing an Earth-like plate tectonic system. First of all, you need plates. So what by plates, we mean the crust and the uppermost part of the mantle, which together constitute the lithosphere. And so their strength properties are very much related to their temperature. So you can't be too hot, or you just don't have rigid plates that will constitute plate tectonics. You also need to have mantle convection. So you can't have the planet, and this is just a very schematic sort of integrated interior planetary temperature. You can't have a planet that's cooled down so much that it no longer has convection. So this would be the window, broadly speaking, for some kind of tectonic system. A big question in the geosciences these days is when, in fact, Earth entered this window. How long plate tectonics as we know it today has been operating, that's really a question for another time. So I'm just showing these cooling curves for Earth, Mars, Mercury, and the Moon in a very schematic way. You also need to kind of stay in this window for at least 1 billion years for the whole system to be able to go through at least one cycle. So we need crispy crust. We need a mobile mantle. And then there's really a third criterion that we have come to appreciate as we get more information from Mars. And that is that the crust cannot become so thick that the convection in the mantle can't move it anymore. So there might be a kind of contrast between what people call active lid and stagnant lid tectonics. And most people think that Mars probably, if it had a tectonic system at all, had a so-called stagnant lid where there was some kind of mantle convection for some period, but it was never able to move plates around in the way that Earth's system works. So let's look more closely at this process of subduction and then the life cycle of ocean crust. So we're very confident that the Earth's mantle, although it's in the solid state, convects as a flowing solid through, and at places like the mid-ocean ridge, Iceland is one of the few places where that ridge stands above sea level. We have upwelling convection currents, decompression, melting occurs, basalt is extruded, and then that basalt progressively cools. And as I said, the key thing that subduction does for the planet is keeps the interior and the exterior of the planet in communication. So really, the ocean lithosphere is involved with the mantle convection. It's not just the mantle convecting, it's also the oceanic lithosphere convecting with the mantle. So this is a schematic drawing of what a mid-ocean ridge looks like. We have upwelling mantle material. It undergoes decompression melting. I'll talk about that briefly in a second. And as soon as this crust forms, there are hydrothermal circulation systems in which seawater flushes through the mid-ocean ridges. And it's been estimated, in fact, that the entire volume of the ocean cycles through these mid-ocean ridges in about 8 million years. And in the process, the ocean, the seawater picks up all kinds of dissolved ions that profoundly affect the chemistry of the entire ocean. So some of the salts in the ocean are coming from land, erosion of rocks, but a substantial fraction of ocean chemistry is accounted for by this process of hydrothermal circulation through the mid-ocean ridges. Then that water that was acquired at the time that the ocean crust was formed returns to the mantle and profoundly affects the viscosity of the mantle. Without the return flow of surface water into the mantle via subduction, mantle convection would probably be ending about now on Earth. The Earth has cooled through time. Lord Kelvin was partly right, but it's still, especially with the assistance of water, able to continue to convect because its viscosity is lowered by the presence of water. And this, in turn, in a fascinating way, protects the hydrosphere-atmosphere system. So this is a little bit complicated, but convection in the mantle, facilitated by water, indirectly protects the atmosphere and hydrosphere by creating a steep temperature gradient at the core mantle boundary. And the core, the outer core in particular, is the site where the magnetic field originates, also through convected motion of the iron-nickel liquid there. That generates the magnetic field, and the magnetic field in turn protects the atmosphere and hydrosphere. So we have this interesting tangle of tectonic processes that are reliant on the hydrosphere, help to reduce the viscosity of the mantle and perpetuate mantle convection, which then facilitates convection in the core, which then generates the magnetic field, which then protects the atmosphere-hydrosphere system. Without the magnetic field, the atmosphere would be stripped away. We would be much more susceptible to the solar wind and cosmic ray bombardment. So to me, this is a really remarkable and subtle aspect of the solid Earth. The other thing that all that subducted water does is generate continents. So this is another schematic picture of a subducting plate. It's carrying the seawater it acquired at birth back into the mantle. And at a certain depth, around 50 kilometers or so, it devolatilizes, it gives up that water. That water then acts as a flux. It greatly reduces the melting temperature of the mantle rocks here and generates partial melts that have very, very different composition, essentially on the road to granite than the mantle. The mantle is made of primarily iron, magnesium, and silicon. And the things that go into making granite are really in trace proportions in the mantle as a whole. But this partial melting that happens as a result of this fluxing of the mantle by water starts distilling out of the mantle something that is very, very different from the bulk mantle. And in particular, so this is kind of depicting the same thing, what we call large ion lithophile elements that include halide elements like potassium and rubidium and sodium, but also high field strength elements, including uranium and thorium and the rare earth elements, are preferentially distilled out in this partial melting process. So this is just a phase diagram showing this is without water, rocks melt at much higher temperature than with water. And so the reintroduction of water into the mantle through the process of subduction lowers the melting temperature, but then also preferentially picks out of the mantle these really otherwise very rare elements that are only trace components of the mantle as a whole. And this is one of the other reasons that Lord Kelvin went wrong. He didn't know about radioactivity, but he also was sampling the most radioactive part of the crust, namely the continents that are full of potassium and rubidium and thorium and uranium. So it's really fascinating. We've now got quite a lot of information from other planets, and we're very confident that granite does not occur on Venus, Mars, or any of the moons, rocky moons of Jupiter. So Earth is the granite planet. And one way of kind of talking about this is to look at the distribution of surface elevations on Mars, Venus, and Earth. So this would just be, of course, there's no sea level on Mars, but we can choose some median value. If you look at the Martian distribution and the Venusian distribution, you see just a unimodal curve. Mars has a huge range of surface elevations. Venus has a kind of narrow range of surface elevations, but both of them basically just have one mode. Earth, in contrast, has these two very distinct modes, and this reflects two very distinct types of crust, and they have different densities. So the continents stand high, they're made of this much lower density material, granite on average, although it's very heterogeneous, and the ocean crust is made of basalt, which is denser and very homogeneous. So Earth, I always tell students, is the granite planet. And it's that granite has been distilled out of the interior of the Earth, the mantle, by that process of water-assisted melting. But now let's think of, why does subduction happen at all? The ocean crust is generated from the mantle. So then how does it become negatively buoyant? How can it go back into the mantle? So the idea here is that even at places like mid-ocean ridges, like Iceland, the mantle does not completely melt. It's still a partial melt. And the process of melting is called decompression melting because we have upwelling convection, and rocks, being normal substances, not like water, have melting temperatures that are increasing with pressure. So if you have upwelling mantle, you're essentially just depressurizing solid rock coming up. And if you cross over the melting curve, then you get some partial melt. Because different minerals melt at different temperatures, that's why we don't get full melting. So basalt is not the same composition as the rest of the mantle. This is a nice illustration of that from Hawaii. This is the lava basalt that's being extruded there. And this is an inclusion of unmelted refractory mantle material made mainly of the mineral olivine. So basalt is what comes out, and it's the low melting temperature material generated in decompression melting. It's richer in silicon and especially aluminum than the mantle itself. And that's the key to subduction, because when this basalt cools down and begins to be neutrally buoyant with respect to the mantle, at the depth around where it starts devolatilizing, it changes to something entirely different. One of the most beautiful rocks in the world, called eclogite. It was first discovered in the Austrian Alps. And the key reason that eclogite is important is that the aluminum that's in the basalt changes to a much denser version. In basalt, it's in the form of feldspars. It's bonded with other things, but forms feldspar minerals. Then at these depths where eclogite forms and the slab is dewatering, it forms garnets. And garnet is a very dense phase and is dense enough to make this slab, which is made of basalt that came out of the mantle, now denser than the mantle from which it came. And so this chart on the bottom shows the density of eclogite in green with two different models for the the density of mantle rocks at different depths. And at least, except for this little spot, eclogite is always denser. And this is really what drives subduction. If that weren't true, we would not have this amazing recycling process of lithospheric subduction. And the power of granite is illustrated, or garnet is illustrated here. If we look at the spreading rates in the Pacific Ocean versus the Atlantic Ocean, they're order of magnitude different. The Atlantic is spreading very, very slowly. So this is, the colors here indicate the ages. And so in the same period of time represented by the red here, you can see how much more the Pacific Ocean has spread. And the difference between these two ocean basins is that the Pacific Ocean basin is ringed, as I'm sure people have heard, by this ring of fire. All of these margins are subduction zones, where the slab is being pulled down into the mantle essentially by the density of garnet in eclogite. Whereas around the Atlantic margins, there's only one subduction zone here, and there's one in the Caribbean region. So their mantle convection, ridge push, is having to do all the work. So the different forces that are involved in plate tectonics, it's clear that slab pull driven by the garnet in eclogite is the most powerful one. And it's really the plates in this case, not the mantle itself, driving the rate of plate motion. One final thought that I want to explore is the remarkable fact that it seems that for billions of years, probably at least 2 billion, the relative volumes of continental and ocean crust have remained about the same. And this isn't so surprising for ocean crust because, as we've talked about, the process of its formation at seafloor spreading centers like the mid-ocean ridges is pretty much directly linked with its subduction. It has a very simple life. It's born at the ridges, it cools, reaches kind of neutral buoyancy, starts subducting, then changes to eclogite. Okay, so that makes sense. You have to kind of keep those things balanced. The typical lifespan, the time it takes for ocean crust to form, cool, and then be recycled is about 150 million years. But it's more surprising that the volume of continental crust seems also to have been constant for at least a couple of billion years. And this is too much to go into in detail, but there are many models for the change in the volume of continental crust over time. This one happens to focus on argon isotopes. Argon-40 is produced by decay of potassium-40. Again, potassium is strongly concentrated into the continental crust, so you can use argon isotope ratios as kind of a proxy for the volume of continental crust over time. So this is showing the formation of the Earth to today. This is the modern volume of continental crust, and most of these models are showing that by about 2 billion years ago, we had close to the modern volume of continental crust, and now we've kind of remained in this steady state. But we know that new crust is being created, so somehow we must be getting rid of continental crust. But it's not easy to do that. So the average, the kind of residence time of continental crust is about 2.8 billion years. Again, contrast that with 150 million years for ocean crust. And that reflects the fact it is hard to get rid of. Continents can't be subducted. The granite is much, much less dense than the mantles. They're not going to go down. And we can just look at the Himalaya as an example, where we have the Indian plate trying to be subducted beneath the Asian plate, and it's not working. And so we basically have doubly thickened continental crust in the Himalaya. So how can we get rid of continental crust? Well, students always say, well, erosion. Okay, that's true. And erosion is most ferocious in places like the Himalaya, where there's the most topography. But that really doesn't solve the problem, because most of the sediments that are eroded from the continents get lodged on the continental shelves, which are this interesting sort of netherworld between land and sea. So this is that hypsometric curve I showed before, the bimodal curve, continents and oceans. And here's sea level. And you can see that some of the material that we would call continental, in the sense that it's granite, lies below sea level. And this would be the mode for true ocean crust. So this is what we mean by the continental shelves, that part of the continents that happen to be below sea level given the modern sea level. And most of the sediments that are coming off continents that get eroded just get stuck here. So they're still part of the continent. They're not subductible. So we need some kind of mechanism that can shake those sediments off the shelf, get them down into the deep sea floor. And indeed, there is such a mechanism, and they're called turbidity currents. They're slurries, probably rather sudden and violent events, landslides essentially, may be triggered by earthquakes that send huge amounts of continental shelf sediment out onto the seafloor, where they accumulate over time in these great submarine fans. Those sediments now are on ocean crust and have a chance of taking the conveyor down into a subduction zone. And it's remarkable to me that this kind of multi-stage process, erosion, getting lodged on the continental shelf for a while, and then these episodic landslides or submarine avalanches carry enough continentally derived sediment to the deep ocean over time to essentially keep us in a steady state. So even as we're forming new continental crust at subduction zones, we're destroying it through this rather elaborate process at about the same rate. That's amazing. And then the other thing that's astonishing to me about the continental shelves is that these are the places, these are the archives of the Earth. Exposed continents mainly don't make it into the rock record. Erosion prevails. So you don't have many sedimentary rocks that are actually forming above sea level. There are some exceptions. Most sedimentary rocks that actually get preserved in the rock record are formed on continental shelves because erosion, they're safe from erosion. And so these kinds of rocks that were formed on continental shelves are really the archives we look to for information about the evolution of the atmosphere and hydrosphere and the biosphere. That's where all the fossils that we have come from, primarily continental shelf sediments. And most of those would remain inaccessible to us, except for, I guess, oil companies drilling into them. But processes of tectonics tend to shove these continental shelf sediments back up onto the continents in places like the Rocky Mountains in Montana in the United States, where they're conveniently exposed for geologists to see without having to be in scuba diving gear. So a remarkable thing, it's almost like the Earth wants to be read. That you could imagine a planet that destroyed its archives more efficiently, or just never had the right processes to keep a detailed record of what has happened. But this planet does. We have now a pretty good sense of the last 4 billion years, and it's a remarkable thing, and it's a very long text. So I'm hoping that I've made the Earth feel a little bit unfamiliar to you, and I'm very, very happy to answer questions. Thank you.